So this is going to be the second lecture series. Like I'll give the first and last talk, and then Toby mainly talk about the local Langlands, but L not equal to P case, and Toby give the second and third lecture can talk about the more complicated L equal to P case. Okay, so let's start. So let's first recall the classical local Langlands correspondence, which when I say for F is a non-Archimedean local field, or QP, finite extension of QP, or FP double parenthesis T, and G connected reductive group. Over F. By the way, it's like size of the is okay, visible at the. Okay, so record the. Let's see. Very roughly speaking, the classical local Langlands correspondence is that there's it's kind of one way to think about it is a classification of irreducible smooth irreducible representations. Of this periodic group G of F with some coefficient. Let's see. At the beginning of the theory, it says with C coefficient, but of course, for arithmetic applications, you want to also consider some other coefficients like FL, FP. But very roughly speaking, this is such data. This set of representations are parameterized by the so-called admissible representations of the Wei group, or maybe some Wei-Delin group, maybe GA to the so-called Langlands Zhu group, or maybe L of G, and so admissible representation here, there's some condition. For example, you want this map is sort of continuous in the here we see with discrete topology here with like the usual topology. Here you want a forbidden map semi-simple here, and this GA map to some unipotent element. Sorry, I think it's okay. This is very, at the beginning, this is a very rough thing, but this is, turns out more or less, this is correct when G is GON. This is okay due to basically, this is the theorem. I mean, basically here, I probably need to up to G hat conjugacy, and this theorem, I think this is due to one characteristic is bigger than 0. It's due to Lamont, Rappaport, and Spooner, and characteristic 0. This is Harris-Taylor, and yeah. Okay, but when G is general, such statement is far from being precise. So on the dual side, I usually then people realize. By the way, such homomorphism are called nowadays called the L parameter, L homomorphism, or L parameter or Langlands parameter. So on the dual side, usually people realize then this map is in general not gonna be like a 1-to-1 there several things will map to the same representation, but then they can be further distinguished, separated by consider additional data. People sometimes call the enhanced Langlands parameter, which the additional data is sometimes you need a representation of the centralizer group of the Langlands parameter. You need to add. So, for example, I think the first result in this direction is this Kashtan-Lustig's result of classifying representations with Iwahori fixed vectors. Then they actually, for each such representation, they produced like a triples, such as the Kashtan-Lustig. So from like representations with Iwahori fixed vectors to such triples, like not triple, just pairs. Why I say triple? Of rho and phi. But on the left hand side, actually, it's also, even you enhance the right hand side, the left hand side is also not quite correct. Then nowadays, people realize that one needs to consider not just a representation of G itself, but the several. It's like maybe there's a kind of a decoration, maybe extended, or maybe pure inner forms. Maybe one needs to consider representations of G. So, for example, then you need to probably put all of them together, all such representation together. Then it has a better, like a parameterization. The parameterization looks much better. Of course, you can just consider one of them, but then this you will miss something here, and this parameterization will look very complicated. Okay, so this is very brief review of the classical story. I'm not gonna make this. By the way, how can I get this? I see. Is it too? Okay. It's always hard to work with. Okay. All right. So okay. Yeah, that's fine. So now let's. But if you look at the structure of this correspondence, this is on the right hand side. It's apparently what the. If you think no little bit algebraic stack, actually the right hand side is not really. It looks very much like a stack structure. It's basically you are considering some object with some automorphisms, and you are considering sort of irreducible representations of this centralizer group is sort of basically the category like quasi-coherent shifts on the point module of the group. So therefore, it's really the structure of this, like if you just look at the form of this correspondence, it has some like a sort of a categorical structure there. And also the left-hand side, okay, that's a little bit hard to, more difficult to see that. But when once you put different groups together, actually there's also like there's some kind of actually geometric structure among different groups. So this just in this classic form, there's supposed to be some actually there should be some categorical correspondence actually lands behind even such classic correspondence. So I think one of the goals of the lectures, sort of hopefully today I will at least make some kind of statement, some enhancement of this and conjectural enhancement of this form of this correspondence, and maybe give some evidence, and maybe that's what I was trying to do today. Okay, so the first to make this really work, the first thing is actually we need to some geometrical objects on the dual side, sort of parameterize all Langlands parameters, and there's so then let's start from the stack of L parameters. So so let me just see the following. So let's see the following theorem, which due to that Helm, Finnick, Moss, independently Farks shelter, and also by myself. So it said that actually there exists an algebraic stack maybe X G, let's say over ZL, classifying continuous L parameters, so homomorphisms rho from the Wei group of F to the so-called Langlands dual group, or actually, because if I want to make it over ZL, I need to modify it a little bit, so-called the C group of G up to G hat conjugacy. So I will basically explain some term more precisely. And this is X, maybe also say some property. X is a local complete intersection of relative dimension flat of relative dimension 0 over 0. Okay, so let me see a little bit precisely what does this first what does this mean? So first of all, the easy thing is maybe to see this definition of a C group of G, which is basically slight variant of the L group of G, which is, I hope in the summer school it's okay to, I already mentioned there, but I hope it's okay, everybody. No set. This is a Langlands semi-direct product of the Langlands dual group of some finite Galois group of F, where F tilde is sort of like a sort of some, I don't know, splitting field of G. May not be splitting, but you know, like the Galois, if you have a reductive group, then the Galois group of F acts on the root system, and then you take some extensions to the Galois group act. I mean, this action factors through some finite extension, finite quotient. So then C group actually it's so here this guy is actually there's natural action. This is a slight variant is defined as this guy which is almost the same, but here you also consider action of GM, where GM acts on G hat by so-called the half sum of co-roots to the adjoint form, which acts also G hat. So consider such thing. So if you don't see this people, it maps of order. So this is a half sum of positive co-root. So if you didn't see this before, it doesn't really matter. You lose really less, not much when you just consider L of G when you're working L not equal to P. It's sort of probably only important when you work with L equals P, and maybe globally you really want this. But I mean, for most of the talk, you can safely just think about this. Okay, so and then what is there any questions or what is continuous? This is slightly subtle. So we want to basically define some algebraic stack over ZL. So I want to say for every ZL algebra A, I need to specify some like a continuous map from V group to let's say even consider G hat is split. G is split. You want to specify some map from rho to G hat of A. So let ZL algebra a map rho. Let's say even just because everything then can be embedded into GN. So we can indulge this with a then this is I mean I can embed the G hat into GN, just need to specify what is this is a continuous. It's called continuous if, let's see, each vector for each vector V, each element in V to the n, the V group acts on here, rho WFV generates a finite generated ZL module. Okay, so that's so remark, and then by the way, when I see the stack, then this guy is really just we'll consider all such thing. You know. Then such you want two conditions such that the modulo G hat of A. Then of course this is first. I need to modify this, add this a little bit. First, you want to when you talk about stack, usually it's not. It's it's A value point is not going to be something modulo it, but up to shiftification, right? Shiftification. And the second is in the usual definition of a Langlands parameter, L parameter, you want this composition to the factor. For example, this second factor, you want this is to be the natural projection, and you want to basically, for example, with the first factor. This is the second factor is natural projection. The first factor is usually think cyclotomic character, probably inverse cyclotomic character. Okay, so that's a precise definition of such a algebraic stack. Is it okay? I mean, this is a definition. So let me just compare this with say a little bit. Repeat. Continue. I give a definition. Is that the usual. Yeah, I will give several remarks. Okay. Let me just give several remarks. Okay. So. Huh? I think it's okay. Yeah, it's okay. Yeah, it's automatic. Oh, right. Okay, yes, that's right. This is correct. Yeah. Okay, so let me just make several remarks. First, compare with classical thing, and then say a little bit about the general. Okay, let me erase this. Continue it, and then say a little bit. Oh, by the way, is there a place I can see the time? Because oh, I see. Okay. Huh? Cyclotron. Okay, so several remarks. First of all, is if A is the classical, some like finite extension of QL, so this is the usual thing. Finite extension of QL. This is the usual thing, usual continuity condition. If A is QL bar, actually, then it's it would be easy to say actually this guy actually automatically factors through some finite extension of QL. Factors through some F over QL. This, of course, in when people study continuous representation of profinite group, such kind of statement was proved can be also proved using this Bayer category theorem. But in this definition, it's sort of automatic. The third is A general. You can also do this. You can endow A with this topology. So maybe it's like a kind of incompletion of analytic topology. Then this becomes like a sort of continuous with this analytic topology. But I should probably mention that when A is equipped, meaning you write A as an inductive limit of finite general Z modules, and endow with for each finite general one is usual analytic topology, and endow the whole thing with an inductive limit. So then this continuity just becomes a usual continuity. But the problem is, of course, when you equip the ring with such topology, it's not a topological ring in the usual sense. it's nevertheless like a ring object in the category of compact generated space, or maybe nowadays better is called ring object in the a condensed rings. So, but anyway, you can do that. So that's just the remark with this continuity. But the nice feature of you find this stack is now if you go back to the classical thing, somehow you will not need this GM here, and also not the phi here. This GM will come from this usual Grothendieck's local monodromy theorem. When you talk about continuous Galois representation, you can get a Denis representation by talking about taking the logarithmic of 10 Galois generator. But but this phi, like the representation of centralizer, actually it's sort of this guy is okay. Somehow later we'll see. Later we'll mention it will then build into the geometry of this geometrical object. So you don't really need this extra data when you formulate. So let's look at a little bit about the geometry. See a little bit about the geometry. Yeah, maybe some geometry. This. So first of all, maybe maybe because this is stack. Usually stack is kind of hard to visualize. Maybe I first add the box, which just classify all such homomorphisms. So it's kind of the frame the Langlands parameter or whatever. Okay, and the X is the quotient at. So this guy actually, first of all, this is actually an affine scheme, locally finite type, disjoint union. Of finite type. No, it's a disjoint union of finite type affine schemes. I just switch the order of finite type affine schemes over ZL. And because the stack is zero dimensional, so this is going to be, of course, relative dimension G hat. Its completion at some, let's say, rho, some particular, given some point, let's see, some field value point, let's say cap, is the deformation ring, the usual deformation ring, framed deformation ring, which will actually also, I believe, discuss somehow in the afternoon, probably. Let's say rho bar or whatever. Okay, so this is local thing, and let's say global. It usually, let's say at least the G, let's say, so-called unramified, maybe or meaning quasi-split and the split over unramified extension. Then such thing, such stack or you can add the box or not, doesn't matter. Classifying. So I'll give you a little bit the feeling how this look like in the. So it contains an open closed substack and closed. We call the tame part, and then it has something like the unipotent part, and then there's something like the unramified part. So this is just consider those representations rho such that it factors through the tame quotient of the Wei group, and now the tame quotient of the Wei group is topological group is essentially generated by two elements. Yeah, it's if you choose some generators, you can write this is like a how sigma with this relation sigma tau sigma inverse is tau to the q's power. This is sort of a dense subgroup of inside here. Take this profinite completion, you get this. So it turns out that this stack, you can just, once you choose such generators, you can write this just basically classify two pairs of elements in the two group satisfying this relation. Okay, so then you can see it's really nicely, it can be defined, you pick up two generators. So it's really an affine scheme, right? You pick up, it's some sub-scheme means I'm like G hat times G hat satisfying certain questions. So it's, inside here, you want this row of, here, this is classifies those, the tame inertia is unipotent. And this definition is not very good unless this is in general, unless this is if over QL, this is also a connect component. I still write connected component, but it's not irreducible. It has several irreducible components. This guy, and then the unramified part is basically one irreducible component. It's given by those representations such that the action is factored through just it's trivially on the inertia. So it becomes just a map from Z to sort of G hat. So then this is just the G hat, more or less. Okay, up to slight modification, you require these conditions. So unipotent part is you require rho of tau is unipotent.
Is a connected component or it has several?
It's a connected component in over QL. Yeah, but it has some different irreducible components. I'll just draw a picture in the case of a picture.
The TG of what? What is the bracket? The image of the row bar.
Row bar.
Oh, GOK.
Kappa or K or kappa field, some field, some like a some field over ZL. Maybe it could be FL or some QL. So particular example is G is the simplest example is G is PGL2. So G hat is SL2, and in fact in this case you can also know the C group is basically GL2. In this case, like this, I'll just draw this unipotent part. Has two inside here, this unramified part has this guy is basically G hat mod G hat. So it's like so it's smooth at least. If you choose some over some particular points, for example, some nice points, actually you can reduce this to something more GM. So anyway, and for example, there's a particular yeah, let's say P is a residue. Let's say this is F is just a QP. So over here, it turns out this has another component. So this is unramified. And then this is it has another component which they meet at this point, crystal matrix 1P1. This is so-called Steinberg. And this classifies this row of tau is not one, but it is sort of conjugate to 1,1,1,1. And then the meet at here. And actually the local equation, really the stack is as soon as L not divide, I always get the write it bigger. Which one? It's anyway, so
Please.
yeah, but I supposed to the 12:30 or something. Yeah. Okay. I have time. P1 is a matrix, right? Inside this is a G hat. It's like a 2x2 matrix. Yeah. Yeah. There's a particular point inside here. So okay. So this local geometries really look like this. I just up to look like this modulo. Like if this is X coordinate, this is Y coordinate, this is a GM. This is GM X by weight 2. This is the case when L does not divide, let's say, P. I think the other way around. Oh, okay. P plus or minus 1 there. More. Oh, yeah. More X. This is the intersection X, Y equals 0. Then the whole thing modulo GM. This is kind of the picture. Okay. Yes. X is ST stands for Steinberg. Steinberg. So this is just something I labeled the 2 component. Okay. So the stack actually basically has these 2 components. One is called unramified, one is called Steinberg, and as you can imagine, has something to do with the Steinberg representation. Huh? On X. By way 2 on X, yeah, and the trivial on Y. Trivially on Y. Yeah. Okay. So GM only X here, not here.
The row tau at the intersection point, row tau is very trivial.
Yeah, here is trivially because this thing is a row tau is trivial. Yeah. Yeah, but those part is like the row tau is this. Okay, so this is in general what happens is for each unipotent conjugate class of G hat, you're gonna have 1 component. They meet very complicated in general. So this is a complicated thing. Okay, so anyway, so is that okay? More questions?
Special about the matrix P1.
P1 is the only, if you, let's say if you want to have this relation, sigma inverse of tau to the P, and then if you want a sigma to be, then you will see the trace of sigma must be P plus 1. This will force the trace of sigma is P plus 1, something like that. So, okay. So then you end up with, you can always
don't actually get over G check, but get over P, but both of them are equal to P. Right? So then you have to create a thing about one determinant equal to P.
Yeah, determinant is always is P. Yeah. These two conditions. Then this guy is always conjugate to this. That's the only place you could have a intersection. Yeah. All right. Thanks. Okay, so with this now at least I can start to give some still not very precise form of the categorical Langlands conjectural form, but I can do categorical. So I will only today I will be only stated one form in some form like part of the story. On the left hand side, I still stick to the representation of the G. Hopefully on Friday, after many other lectures, I can see some like how to also enhance the left hand side to be a more. So conjecture is there exists. Yeah, so assume G is quasi-split. So meaning it contains a rational Borel and fix like some pinning and some psi additive character. So maybe like a E in like I don't know, this is called a pinning. The E is you can think about it how do you think? You have B inside here, you have a uniform radical U. E is basically a algebraic homomorphism from U to GA, non-degenerate, meaning like in the case of let's say GON, this is just the upper triangular matrices. This is strictly upper triangular matrices. Any homomorphism or factor through it U, because this GA is additive, such map will factor through U. It's derived U modulo its derived group, and this is some product of GA correspond to simple roots. And then this is non-degenerate. Namely, when you restrict to each root subgroup is non-trivial. And then also you fix psi, some additive character, non-zero. So such data will determine the so-called Whittaker data. So then, okay, so then let's see. There exists a fully faithful embedding. And actually, for simplicity, I will actually only consider QL coefficient here. Otherwise, I need to see something more complicated. And assume consider QL coefficient, maybe QL bar coefficient. So there exists some fully functor from the bounded derived category of representation of category smooth representations of G of F to and I take the finite generated one, those finite generated representations to the category of bounded derived category of coherent shifts on the stack. Leave it for embedding. Okay. It such that satisfying certain condition, this is a like sort of conjecture, satisfying certain conditions, which I will list some of them, but this condition is not enough to uniquely characterize this, but nevertheless tells us this conditions tells us already a lot. Conditions, and I'll list some of the conditions here. Condition one is if G is just the GM, A of G is given by the local class field theory, which I'll first list all the conditions and then explain some of them. What are the concrete the mean? Compatible with so-called taking, let's say G to be G1 times G2. If you have a product two groups, left hand side you can consider the representation of the products. Right hand side you can also then actually there's some nice way to the category will be naturally the tensor product of this two categories separately. So this compatible central isogeny. Basically means it's a map of a reductive group, but it induces isomorphism on adjoint groups. And the weight restriction. Basically what you can show it if on the representation side if G is a weight restriction of another group, let's say G is a weight restriction. Sorry. Then you can show actually the two sides doesn't really change. Both sides are the same. Like reminiscent for like the representation for G, F is gonna be the same. GF is just a G prime F prime. So of course the category doesn't change. You can also show the right hand side the stack of Langlands parameters are for G and the G prime are also isomorphic. So the right hand side doesn't change. 3 is it will send the Whittaker so-called the Whittaker co-modules or Whittaker. Basically, this is a sort of compact induction from the U of F of G of F Q alpha to that's a structure shift. Okay, this needs a little bit of explanation. I will do it later. 4 is parabolic induction compatible with, which I'm gonna explain. And the 5 is sort of if you want to have some global application, some normalization. If G is unramified, from U of F, U. If G is unramified, this guy should send, for unramified, there's an unramified representation. G of O. O is a ring of integers of F, G of F of QL. This should be just the structure sheaf of unramified part. Over QL bar. This is also over QL bar. It's supposed also to be okay to ZL bar, but then, oh, actually, okay. In this case, I don't even, because I only consider finite generated one. I don't even need to. Yeah, I think I can just state this for even for ZL bar. It doesn't really matter in this form. Thing. No. Oh yeah, this is not trivial one, but so maybe I should really write this. This is because I'm trying to come. You take the differential of this. Oh no, not differential. You take the E. E will give you a map from U of F to F, right? And then you compose with psi. That gives you a one-dimensional representation of U of F compatible. Yes. For central isogeny, not arbitrary reductive. If you have an arbitrary reductive group, one map to the other, there's no obvious map on the dual side. But for central isogeny, there is. So this is so this actually says that there's a like map from 2 to. So then you can you can, yeah. Okay, so right. So I think there's a supposed to be certain more conditions, but I would just mention this 5 at the moment, and the comment.
Yes, GOQL 5. What is that?
This is trivial one. Yeah, trivial one. Yeah. Maybe okay. Let me just say trivial. So this is like unramified, unramified. Okay. I shouldn't erase this. Yeah. Maybe. So huh? I talk about I mean, because it's a stack, right? There's some stack issue. This guy actually it's this picture modulo GM, modulo G, G hat, then you can reduce to this. The stack looks like.
The stack is equivalent to that.
Yeah. Okay, I leave the picture here if I have a time, and then I have time. This has something to do with some example, but not sure. So for one, I just remarked is that the category of if G is GM, then the representation, this is always true, but like smooth finite generated smooth representation of G of F, this category, this is always the category of finely derived category of modules over the Heck algebra, like maybe some non-degenerate modules. Here, this is a Heck algebra. Let's just see this finite generated. This is a so if you when G is GM, it turns out the nice thing is this Heck algebra can be easily described as by local class field theory. I mean, what is this Heck algebra? This is just the limit of functions, some compact support functions of F cross modulo 1 plus some congruent subgroup. Right? And then by local class field theory, you know, homomorphism from W group to GM is the same as map from F cross to GM. And so this is basically the functions on X of G. So you can see that. So then this, therefore this equivalence is supposed to send the modules. So H modules then is kind of the finite generated module. It's basically by this local class field theories, or maybe it's kind of the category of quasi-coherent sheaves, or category of coherent sheaves on actually X box. So in this case, the functions on this framed L parameter is already like this. The GMX trivially. So, and this actually embeds into or maybe it's better actually to consider the GIT quotient. Let's do this. And so the equivalent is supposed to be this A of G. This is part one. And of course, from this example, just in the case of GM, you already see that this function is not going to be equivalence of categories. You only get part of the coherent sheaves on the picture. And also I want to don't have the okay. Maybe I just is okay. Is okay. You erase this part. Okay. I want to keep that picture. G is a general torus. GM, yeah, this is an explicit description. Yeah. Yeah, this is like GIT quotient is basically the ring of yeah, you can either take this or frame thing, it's the same. Like the difference is yeah. So XG explicit you can write in this case you can write non-canonical as G is GM. It's like this frame thing times like some BGM. So the coherent sheaf on here would be some part come from here and some more grading. So this representation of G only see like grade zero part, for example. There's some other parts. GIT quotient of the frame thing. This is equivalent to this. This is embedded inside here as degree zero part. Oh, I just because the category of coherence shift here is basically category of coherence shift here plus some, you can shift some grading. It's not so big here, but you already see it's not the equivalence. Yeah, so you are seeing, therefore you see the left hand side, you really miss something, but you can of course add them those things back, but you need more later. Yeah, not today. Okay, now I'm a little bit out. I really want to comment say a little bit about 3, because this is something slightly different from the classical, like 4 parabolic induction. Like 3 is kind of 3, 5 is kind of some normalization, and you're supposed to satisfy. But the 3 is a parabolic induction. Because this is sort of some different from the classical Langlands formulation of classical local Langlands. So recall that if you have a G, if you have a parabolic subgroup, and take M is Levy quotient, then on the representation theory side, you have this representation of M of F, smooth representation. You can do parabolic induction and restriction. So if you suppose you have those equivalents, okay, but not equivalence, sorry. It turns out this fully fitful functor is also on the dual side. You also have some kind of this picture, such induction and restriction, and then this fully fitful functor is supposed to compatible with that. So on the spectral side, like the Galois side, but you also have such picture. But the point here is it's not what you might think in the naive local Langlands, where you embed the L group M hat mapped to G hat, and then it's not induced by the map from M hat to G hat. It turns out what you need is something for this some stack for the parabolic. So similarly defined stack for P. For every parabolic, you have the corresponding parabolic P hat in G hat. Then you can consider continuous maps from V group to P hat, and then there's then basically you have P hat inside the G hat. Go to M hat. Using this, you can induce a picture, and then the parabolic induction restriction I Q is given by some upper Schrick lower star and some adjoint. So then this equivalence is really compatible under this. So this is not what you might think naively, just embed M hat into G hat. Okay. So is it okay? Like this is sort of any questions? Yeah.
It's trivial, yeah.
So it's trivial. Yeah, all of them are. Yeah, it's turns out to be the same. You can use yes. It's trivial. Yeah. So it's like a closed substack irreducible component. You think about its coherent structure shift as a coherent shift on the ambient thing. Like structure shift. Yes, because at least in characteristic zero, the unipotent part is a connected component. So it will be some sort of some idempotent here. It can be described explicitly, but because of time, maybe later after the lecture. Yeah. So okay, so that's roughly the form of this conjectural picture. And if there's no further question, I give some kind of evidence. What's already known.
It's not good on the color side, just for single color representation.
No, it's really for coherent shifts. Yeah. Skyscraper will give you something, yeah, might spread out or something. Something like that. So, of course, this is a looks like some fantasy, but there's some evidence. The first is this big theorem of Farkas and Schotter, which says actually, if you think about it, if such functor exists, then the global functions on this stack will act global functions on the stack will act on any coherent shift, right? So it will act also, therefore, act on this any if there's such fully faithful functor, then it will also act on the representations. So therefore, if such thing exists, then there must be a map from the functions on this stack to endomorphism of the identity functor of the left-hand side, which is like the Bernstein center. You can think Bernstein center. Your F, which you can define as just the endomorphism of the identity functor. Or maybe you can also say it's a endomorphism of this Hecke algebra SG times GF representations. And then since actually there is such a map, ring homomorphism. This is I guess nowadays people denote by spectral Bernstein center ring of functions. So once you have such once you have such map, actually you can already assign the so-called semi-simple Langlands parameters for representations. Say if you have a representation, if it has a central character here, I mean this map goes another way. It goes from the spectrum to like the GIT quotient. So if you have a representation has a central character, give you a point here, it will give you like a point here, and this by some theory of pseudo representation it's actually classifies like a semi-simple representation. Up to conjugation. Okay. So I should say, like the conjecture such a map exists. Maybe remark. And some questions? Yeah, maybe. I guess this such map should exist actually was conjectured long time ago, much earlier before this so-called the categorical local Langlands. For example, when G is GON, such thing was known before. First of all, let me make a remark. This works over actually ZL, not just the Q the coefficient. Second, such thing actually exists. Prediction exists a long time ago before this categorical local Langlands conjecture. For example, when G is GON, such thing was constructed by origin Helm and Moss when for ZL bar, and I guess even for QL bar coefficient, this is even earlier. Probably Peter, you did or maybe even. Yeah, but there's quite a long history about that. But for general group, this is this was in Fox Schultz, and although this map exists in such statement is completely classical, you can actually define such thing without any categories. It's basically say there's a map of rings, but the machinery to produce such map is quite actually has use some categorical nature of both sides. Hopefully I will see something on Friday, but not sure. Time. Okay, so another evidence probably I also want to mention. So you do get some part of this is you do have a really there exists fully faithful functor. I'll call him from category him representation of GM, or some people would call depth zero representation. Category. Sorry, everything needs to be derived. I'm not sure I have time to see that. And part. There exists such a fully faithful functor. Over QL. Over QL. Yeah. And again, yeah, sorry. Also, G is unramified over F. It's such a such fully faithful functor. What does it tells us? Let me just see some content. This basically is the following. Concretely, what does this mean? On the categorical representations, there's a particular class of objects called the compact induced representation K of high. When talk about when depth zero representation, basically this means you have P some paraholic, and it has some Levy quotient, which is finite type reductive group, like finite group of D type, and then it has some representation, finite dimensional representation. Okay. Such thing then will, if under this correspondence, then it will give you some sheaf. Let me denote by A pi. This is some coherent. A priori, this is a coherent complex. May not. But whatever it is, if this functor is fully faithful, that means the endomorphism algebra of this object will be the same as the endomorphism algebra of this object. Therefore, the Hecke algebra, its endomorphism is basically some Hecke algebra. Therefore, its endomorphism will be some Hecke algebra. So this corollary is the endomorphism of this guy will be just the Hecke algebra. Of this one. And of course, if when this curve P is G of O and pi is a trivial representation, this one is what you expect, this structure sheaf of unramified part. So some time is almost over, so let me just make a some remark, or maybe some example. So first, remark one. I should say I strongly, I mean, I'm not say strongly, but I think basically I have a sort of a strategy to prove it, but I haven't checked carefully. A pi is a honest coherent sheaf. Should be. Let me just say should be an honest coherent sheaf. So it's not. It should not be really complex. It's really honest coherent sheaf. Anyway, it's true in many cases, but I think there's some way to prove it in general. So I don't want to even make this a conjecture. So it should be. But this fully faithful functor does not send representations, or let's say only exists in derivedly. It doesn't send an honest representation to an honest coherent sheaf in general. For example, you may ask, what does this functor send the trivial representation to? Let's say in the case G is GO2, PGO2, the simplest case. It turns out that under this equivalence, the trivial representation will send some coherent sheaf supported, completely on the Steinberg component, but in cohomological degree -1. But with some twisted weight 2, so it will. So this is turns out to be the structure sheaf on this Steinberg component, but with weight -2. So in other words, it's going to be the ideal sheaf defining this point. And also shifted to cohomological degree -1. So maybe it's better to normalize in this way. Here, this parenthesis twist means y means weight -1. This is weight -2. Twisted by weight. So structure sheaf has a natural weights, right? Given by this natural weights. You further twist by -2. Yes, I think so. Yeah. And then this one is homological shift. It's sitting homological degree -1. So it really sends a representation to something not in the usual coherent shift. So I guess I'm going to stop here.